Greetings from the Department of ECE. We were discussing about embedded system hardware. In that, only four major components that you have: ARM processors and controller, peripherals, and bus. Under the bus, we were discussing about ARM bus technology. So, embedded systems which uses on-chip bus, which is internal to the chip. So, you can observe here you have majorly it allows different peripheral devices which are to be interconnected with an ARM core. Purpose of bus. So you have three different types of buses: AHB, ASB, and APB. APB indicating ARM peripheral bus. In order to connect to the peripherals with the ARM core, we'll be using APB. ARM system bus and AHB, ARM high performance bus. It is internal. Major difference between AHB and ASB is if we want to transfer a burst of data, then we go with AHB, a high performance bus. And there are two classes of devices which are attached to the bus. One is ARM processor core, which we call it as a master, and the peripherals, which we call it as a slaves. So core indicating, or the master device indicating, it is capable of initiating the data transfer, whereas a peripheral indicating capable of only responding to a transfer request from the bus from master device. Coming to the bus, it has two architectures. One is a physical level, which covers the electrical characteristics and the bus width. So it could be 16-bit bus or 32-bit or 64-bit. Then it follows the protocols. Protocol indicating general rules and regulations that governs the communication between the processor and the peripheral devices. So coming to AMBA bus protocol, AMBA, indicating advanced microcontroller bus architecture, which was introduced in 1996 and is widely used on-chip bus architecture for ARM processors. So it has been introduced with three variants. One is ARM system bus, ARM peripheral bus, and an ARM. Later they have introduced a high performance bus using AMBA. So peripheral designers can reuse the same design on multiple projects. That means you can fit into that can be simply you can bolt into the on-chip bus without having redesigning of an interface for each different processor architecture. That means you can say that plug and play interface for the hardware developers, which improves the time time to the market and the availability. Coming to AHB, it provides a high performance, high data throughput compared to ASB. So it is based on centralized multiplexed bus scheme rather than bidirectional bus scheme, allows to operate at higher clock rates. So ARM has introduced the two variants under AHB, multi-layer AHB and AHB Lite. So multi-layer allows the multiple devices, that is multiple active bus masters. AHB Lite, which is a subset of AHB and is having a single bus master. So majorly AHB is used for high performance peripherals, APB for slower peripherals, and the third bus for external peripherals. So this is about the bus architecture. Then coming to the memory, any embedded systems, if you consider, which has to have some form of memory to store and execute the code. So you have to compromise with respect to the price, performance, and the power consumption. Depending upon your application, one has to choose that. So specific memory characteristics if you want to get, such that hierarchy, width, and the type, based on the comparison one can go with. So almost all the computers have a memory arrangement in the form of some form of hierarchy. The diagram indicates the fastest memory is a cache memory, but the memory size is less since the cost is high. Main memory, next memory which is next to cache is a main memory, then secondary storage device. The slowest memory is a secondary storage device. Cost is less cost, and you can have a high data storage. Then coming to the cache, usually it is placed in between the main memory and the core processor, which is meant for speeding up the data transfer between the processor and the main memory. Actually, it provides an overall increase in performance, but at the cost of at a price. So main memory, usually it is a large one, around 256 KB or 256 MB, even greater than that, depending on the application one can make use. So load store instructions as means ARM processor uses a RISC architecture which operates with a load store architecture. So accessing the main memory until and unless the value has been stored in a cache, which will make use for a fast access. Secondary storage, the diagram shows here. Between the CPU and main memory, you will have a cache memory. In 3-level cache organization, you have level 1, level 2, level 3, 3-level cache between the CPU core and the main memory. So memory width indicating about the number of bits that memory returns in each access. That means that in every cycle, how many bits that it can transfer at a time. So it could be 8 bit, that depends upon the data, bus width. It could be 8 bit, 16 bit, 32 bit or 64 bit. The memory width directly affects the overall performance as well as the cost ratio. The tabular column, once if you observe, if you are using ARM 32-bit with 8-bit memory, so you need 4 cycles to access 32-bit data. That means 8 into 4, 32. If I use 16-bit memory, that means 16 bits it is transmitting at a time. Then it requires 2 cycles to in ARM 32-bit instruction set. If it is a 32-bit memory, 1 cycle. So in thumb instruction set also same. So 8 into 2, 16-bit, 2 cycles you need. If it is a 16-bit, only 1 cycle. If it is a 32-bit memory, then it is only 1 cycle. So coming to the memory type, there are different memory types you have. You have a read-only memory, flash memory. Already known about this. Then in RAM, random access memory, you have a dynamic RAM and static RAM. In dynamic RAM, the diagram itself indicates you can store the data in a cell along with a capacitor. So it is the lowest cost per megabyte compared to the other RAMs. So it is a dynamic one. That means it needs to have its storage cells to be refreshed when you give new electronic charge for every few milliseconds. So you need a setup time for this DRAM before using that memory. Coming to static RAM, it is a faster one compared to DRAM, costlier one, and does not require any refreshing because you won't use a capacitor over here. Whereas in dynamic RAM you will be using a capacitor. As we know that capacitor loses its energy after some time, so you need to refresh it back. So DRAM cells needs to be refreshing unit. Whereas SRAM no need to have refreshing memory. But cost of SRAM is high. Then you have a SDRAM, synchronous or asynchronous. So one is with running with respect to the clock cycle or not. Then it is a major difference between dynamic RAM and static RAM, made up of capacitors or made up of flip-flops. Data storage in this dynamic RAM is in the form of a charge, whereas in static RAM is in the form of voltage. It is small in size but less expensive, whereas static RAM is large in size but much expensive. You will have a high storage capacity in case of DRAM, low storage capacity in case of SRAM. Coming to the peripherals, so each embedded systems that interact with the outside world need to have some form of peripheral device. It performs input-output functions for the chip by connecting to the other devices or sensors that are off chip. So every peripheral device usually performs a single function and may reside on the chip. Peripherals, which may range from simple serial communication device to a complex wireless communication device. So you will have, along with that, ARM peripherals are memory mapped. So that means the programming interface is a set of memory address register. Along with that, you will have a controllers. So you need a controller to control the memory as well as the interrupt. Majorly two controllers you have in any ARM processor, if you consider: memory controller and interrupt controller. So memory controller, which will control which is used to connect the different types of memory to the processor bus. On power up, the memory controller is configured in hardware, which is allowed to allow a certain memory device to be active. That means usually for initialization of the code to be executed. Some memory devices must be set up by the software. Whereas coming to interrupt controller, when a peripheral or a device requests an attention or it raises an interrupt to the processor, so the interrupt controller provides the programmable governing policy, which allows the software to determine which peripheral or device can interrupt the processor at any specific time by setting the appropriate bits in the interrupt control register. There are majorly two types of interrupt controllers which are available in ARM processor. One is standard interrupt controller, another one is vectored interrupt controller. So in standard interrupt controller, an interrupt signal will be raised to the processor core whenever an external device requests a service. So it can be programmed either to ignore or to mask the individual device or a set of devices. You can either mask it or that means you can ignore that device. So you will have a separate interrupt handler, determines that which device requires service by reading a device bitmap register, which is there in interrupt controller. So next we have is a vectored interrupt controller. It is more powerful than standard interrupt controller because this will give a prioritize the interrupts. That means giving importance for the highest priority circuit and simplifies the determination of which device has caused the interrupt. So with this we have completed about embedded system hardware. Thank you. Next class we will look into ARM core data flow model, then continuation. Thank you.